Hello, welcome to Module 20 of the course on pericyclic reactions and organic photochemistry. In this module, we will consider 2,3 sigmatropic rearrangement. 2,3 sigmatropic rearrangement is a very important rearrangement because it allows you to synthesize several different types of molecules, as we can see in some of these examples here. Now, what is a 2,3 sigmatropic rearrangement is explained in a generic manner in this particular scheme. If X and Y group are heteroatom group, you can consider, for example, an allyl sulfoxide or an allyl amine oxide kind of a system. When they undergo the rearrangement by breaking of the CX bond here, resulting in the migration of the Y group onto the 3 position, that constitutes a 2,3 sigmatropic rearrangement. These are 6 electron cyclizations. 2 sigma electrons of the bond that is breaking, 2 pi electrons of the XY bond, and the 2 pi electrons of the 2,3 carbon-carbon bond in this particular instance. So overall they are 6 electron involving 6 electron rearrangement. According to the Woodward-Hoffmann rule, they should occur in a suprafacial manner with retention of stereochemistry of the migrating group, as we saw in the earlier examples of 3,3 sigmatropic rearrangement also. These reactions take place through a 6 electron 5-membered cyclic transition state, because you can see the connectivity is between 2 and 3, so overall it will be a 5-membered ring cyclic transition state in the general form it is shown in this particular example. Now the most interesting example or most common example, which is also the first example of the rearrangement of the type 2,3 rearrangement, is of sulfur ylide. If we consider a sulfonium salt, which is a diallyl sulfonium salt in this particular case, this is a symmetrical molecule because both the groups are allyl groups, dimethyl substituted allyl groups. When it is treated with sodium methoxide, it generates an ylide, which is this particular deprotonation from this particular carbon results in the formation of a sulfur ylide. It doesn't matter whether you deprotonate from this carbon or this carbon, it will essentially yield the same ylide. On the other hand, deprotonation from the alpha hydrogen of the ethyl group will give another ylide, which is not a 2,3 sigmatropic system. So this is a 2,3 sigmatropic system. This is allyl sulfur ylide is what we are considering. If we consider the XY group here, we can call the XY group to be carbon and sulfur. Instead of writing as a zwitterionic structure like this, one can always write a carbon sulfur double bond here to illustrate the point that you have a XY double bond in this particular case. The carbon sulfur double bond can also be used as a representation of this ylide. 2,3 sigmatropic rearrangement takes place by the attachment of this carbon to this carbon with a simultaneous breaking of this carbon sulfur bond in this particular case, resulting in the formation of a sulfide. So this is the 2,3 sigmatropic rearrangement of diallyl ethyl sulfonium salt going through an ylide. The ylide is what is undergoing the 2,3 sigmatropic rearrangement. Now this is a sulfonium salt with 3 different alkyl groups substituted. This one of the alkyl group is a allyl group, another alkyl group is a ethyl group, the third alkyl group is a 2-adamantyl group, for example. When the reagent is treated with tertiary butoxide, the ylide is formed with respect to the ethyl group here, which constitutes a 2,3 sigmatropic shift system here. This alpha position doesn't have any kind of a hydrogen, so there is no problem here. This is a chiral sulfonium salt because of the fact there are 3 different alkyl groups attached to the sulfur center. So the ylide that is generated is undergoing a very enantiomer selective. This is a first order kind of a chiral induction is what is taking place because an optically pure compound is undergoing the 2,3 sigmatropic rearrangement to give the sulfide. The sulfide that is formed in about 94% enantiomeric excess in this particular case of the chiral centers that is generated in this particular carbon here. So this is a first example of an enantiomer selective 2,3 sigmatropic rearrangement of a chiral sulfur ylide. The sulfonium salt itself is chiral, that is why the induction of chirality takes place quite readily in a first order manner in this particular case. Now here is an example of generation of a sulfonium ylide by the carbene transfer. In other words, for example, in this particular case, you have an alpha diazo ester as the reagent. The catalyst used is copper triflate. Initially, the nitrogen is lost and the carbene that is generated is attached to the metal. So you get a metallocarbene species. Metal carbonide is a species that is formed, and the metal carbonide transfers the carbene onto the sulfur. in generating the yelid. When the neutral sulfur and the carbene react together, the sulfur donates the electron to the electron deficient carbene, so the sulfur acquires a positive charge and the carbene center carbon acquires a negative charge, in this particular case this particular carbon. So automatically the yelid is formed by transfer of a carbene onto a sulfur center, and that constitutes a 2,3 sigmatropic shift system. The skeleton is suitable for a 2,3 sigmatropic shift. So 2,3 sigmatropic shift takes place essentially. The copper salt that is used is a copper triflate that is complex to a chiral ligand like this. So the carbene transfer takes place in a very enantioselective manner to produce a particular enantiomer of this particular sulfur yelid that undergoes enantioselective 2,3 sigmatropic rearrangement to give in 62% chemical yield and 52% enantiomeric excess of this particular sulfide, where this chiral center is the configuration that we are enantioselectively producing in this particular rearrangement. One can also use several different types of metal complexes to generate. We can use ruthenium, rhenium, any copper, rhodium kind of metals to transfer the carbene from a diazo derivative to the corresponding sulfur center. In this particular case, a resolvable chiral rhenium complex is used as a chiral auxiliary. This rhenium center is a chiral center and it is a resolvable complex, so enantiomerically pure compound can be taken in this particular case, and that is coordinated to the sulfur to produce essentially this sulfonium kind of a salt. This is a diallyl sulfonium kind of a salt, except it is, instead of sulfur bearing the positive charge, the rhenium is bearing the positive charge. The oxidation state of rhenium here is different from the oxidation state here. And the oxidation state here is +2, and probably here the oxidation state is again +2. If you represent it as a sulfonium ion, it would be +2 in this particular case also. The rhenium center is a chiral center, so the yelid that is generated is undergoing a stereoselective 2,3 sigmatropic rearrangement to produce this sulfide. The sulfide can be now methylated to using can be made into a triflate by treatment with methyl triflate, for example, with a simultaneous methylation of the sulfur. So treatment of this complex with methyl triflate produces the S-methyl derivative in an optically pure form to the extent of about 92% enantiomeric excess, with a chemical yield of about 78% in this particular case. So here is an example where the resolvable chiral rhenium complex is used as a chiral auxiliary. It is initially attached to the sulfur, and after methylation it is removed in the form of a triflate salt and it is regenerated to get the starting material back in this particular case. So it is truly used in a stoichiometric amount as a chiral resolvable chiral auxiliary is what is used in this particular case, the rhenium salt. 2-3 shifts of propargylic system is illustrated in this particular example. Instead of having diallyl sulfide, you can have dipropargyl sulfide or selenide, as the case may be. When it's reacted with diazo bicycloundecane, which is a base, the yelid is generated. The yelid generated undergoes 2,3 sigmatropic rearrangement to produce an allene derivative. In other words, alpha alkynyl substituted allene derivative is what is produced as a result of the 2,3 sigmatropic rearrangement of the system. Here is another example of ring expansion reaction using 2,3 sigmatropic rearrangement. Once again, the copper carbenoid is generated by the reaction of the alpha diazo ester. In this particular case, the copper transfers the carbene that is generated onto the sulfur to produce the corresponding sulfur yelid. The sulfur yelid is now located to undergo the 2,3 sigmatropic rearrangement as it is shown by means of arrows in this particular scheme, resulting in the formation of breaking of this carbon-sulfur bond and the formation of this carbon-carbon bond, resulting in an enlarged structure, ring expanded structure. In this particular case, a 8-membered ring with the sulfur is what is generated during the course of the 2,3 sigmatropic rearrangement. Here is another structure which is a 7 plus 3 10-membered ring is what is generated here. Initially, this particular sulfonium salt with an allyl derivative, which is this vinyl derivative, is actually a S-allyl derivative. When it is treated with the potassium tertiary butoxide, it generates the enolate, which is not genolate, the sulfur yelid in the alpha position that cannot undergo any rearrangement. The yelid that is generated from the deprotonation of the methyl hydrogen, of course, can undergo 2,3 sigmatropic rearrangement. So these two sulfur yelids are in equilibrium. One of the yelid is undergoing a 2,3 sigmatropic shift, pushing the equilibrium towards the right side, towards the formation of this particular derivative, which is a 10-membered ring system in this particular case, by a 2,3 sigmatropic rearrangement of the sulfur yelid. Sulfoxides also undergo 2,3 sigmatropic rearrangement provided they are allyl sulfoxides. Here is an example of an allyl sulfoxide undergoing a 2,3 sigmatropic rearrangement. The allyl sulfoxide undergo 2,3 sigmatropic rearrangement at a much lower temperature compared to the sulfur ylide derivative, allyl sulfur ylide derivative. This is known as the Mislow-Evans rearrangement of allyl sulfoxides. You can see here the allyl sulfoxide undergoes 2,3 rearrangement. The carbon-sulfur bond is broken and the oxygen-carbon bond is formed to give a sulfinate ester. The sulfinate ester, of course, undergo desulfurization when it is treated with trimethyl phosphate, produce the trimethyl corresponding trimethyl phosphine sulfide. Phosphorus sulfide is what is produced here, and the corresponding allyl alcohol is produced. So the allyl sulfoxide actually acts as a precursor to produce the allyl alcohol. So this constitutes the synthesis of an allyl alcohol through the formation of an allyl sulfoxide undergoing a rearrangement followed by desulfurization to give the allyl alcohol. So this methodology is known as the Mislow-Evans rearrangement of allyl sulfoxide. It's also a methodology for the synthesis of allyl alcohol derivatives using this particular rearrangement. And that is illustrated in a diastereoselective manner in this particular case. This allyl sulfoxide, which is an exomethylene derivative of the 4-tertiary butyl cyclohexyl derivative, the sulfoxide can approach this double bond either from the equatorial phase or swing it around and get it from the axial phase. Of course, swinging it around and getting it through the axial phase will be sterically more hindered. So these are the two sulfinates that are produced by a 2,3 sigmatropic rearrangement. This is the carbon sulfur bond that is broken, and the carbon oxygen bond that is formed is this particular bond. So this is 1, 2, 1, 2, 3, 2,3 sigmatropic rearrangement produces these two sulfinates. Desulfurization using trimethyl phosphide gives the tertiary alcohols, which are shown here. The equatorial approached rearrangement is the predominant rearrangement, occurring to an extent of about 92%. The axial approach produces 8% of the other product. Overall yield is about 99%. So this constitutes a diastereoselective synthesis of an allyl alcohol, tertiary alcohol, in a very diastereoselective manner. Only the equatorial alcohol is formed in major amount. The axial alcohol is produced in a very small amount in this particular case. Instead of sulfur, one can also use selenium oxide to make it undergo the 2,3 sigmatropic rearrangement as it is shown here. The selenium oxide in fact undergoes 2,3 sigmatropic rearrangement at much lower temperature compared to the sulfoxide, allyl sulfoxide. So here is an example of an allyl selenoxide undergoing a rearrangement to give the selenite. The selenite is hydrolyzed to give the corresponding allyl alcohol. This is illustrated by making use of this reagent. This selenide is treated with hydrogen peroxide to produce the corresponding selenoxide. The selenoxide undergoes 2,3 sigmatropic rearrangement to give the selenite. The selenite is hydrolyzed to give the corresponding allyl alcohol. So you can see the functionalization of this position, which is 3 carbon away from the carbon-selenium bond, is essentially used for the synthesis of this type of allyl alcohol in a stereoselective manner. If the sulfoxide can be generated in an enantiospecific manner using Sharpless kind of a reagent, Sharpless oxidation is nothing but the oxidation of a olefin using a titanium tetraisopropoxide as a metal template, diethyl tartrate as a chiral template, and then tertiary butyl hydroperoxide as a oxidizing agent. The same reagent can be used for the oxidation of the selenite to the corresponding selenoxide in an enantioselective manner. Once you have synthesized the selenoxide in an enantioselective manner, the rearrangement can also be expected to undergo in an enantioselective manner. In fact, the rearrangement of the selenoxide that is produced, the chiral selenoxide that is produced from this selenide using Sharpless oxidant. This Sharpless oxidant is same as the reagent that is used for Sharpless oxidation. So please look it up. It is a combination of diethyl tartrate with titanium tetraisopropoxide and tertiary butyl hydroperoxide as the oxidant. So the chiral selenoxide undergoes the 2,3 sigmatropic rearrangement. The carbon selenide bond is broken. The oxygen selenide bond is formed here in this particular case, resulting in the formation of an enantioselective formation of this allyl alcohol. So asymmetric synthesis of allyl alcohol is possible by means of a selenoxide or a sulfoxide rearrangement by a 2,3 sigmatropic rearrangement. Synthetically extremely useful rearrangement. You can see here the temperature at which the reaction takes place is a very low temperature, so one can expect a very high enantioselectivity in this kind of a situation. Instead of using a sulfoxide, which is a chiral sulfoxide. The chiral auxiliary is used in the form of a planar chiral auxiliary, which is the 2,2-paracyclophane derivative, or the 1,2-disubstituted ferrocene derivative, which is a selenide in this particular case. So the aryl group that is present in the system is essentially this group, which forms the diselenide bridge. In other words, there is a selenium already present in the allyl selenide. The aryl group also has a selenide, so it will be a diselenide kind of a derivative here. MCBB oxidation of the selenium to the corresponding selenoxide followed by 2,3 sigmatropic rearrangement enantioselectively selectively produces this particular allyl alcohol. In this case, rearrangement is very specific to only this allylic position, not to this double bond here, resulting in the formation of the terminal allyl alcohol in this particular case. So the planar chiral auxiliary are the 2,2-paracyclophane derivative or the ferrocene derivative, which are used for chiral induction in this particular instance of rearrangement. Another example of a diastereoselective selenoxide rearrangement is shown here. This selenide, under the reaction conditions of hydrogen peroxide as an oxidant, produces a corresponding selenoxide. That selenoxide is an allyl selenoxide, so it undergoes 2,3 sigmatropic rearrangement to produce the corresponding selenite, which can be hydrolyzed to give the corresponding hydroxy functional group. You can see as stereochemistry is beta in this particular case. The alcohol that is produced is also beta, which indicates that superficial migration has taken place, resulting in the formation of a particular diastereoisomer, which is shown in this case. Again, the reaction is carried out at a very low temperature, ensuring the high diastereoselectivity of this particular reaction in this particular case. Instead of sulfur and selenium, one can also use nitrogen center. The nitrogen ylides also undergo the 2,3 sigmatropic rearrangement. These are examples of nitrogen ylide undergoing 2,3 sigmatropic rearrangement. When this ammonium salt is treated with sodium hydride, two reactions take place. The first reaction is the generation of an ylide, followed by a 2,3 sigmatropic rearrangement to form this particular product, which is arising from the skeletal rearrangement of the piperidinium ring to the corresponding pyrrolidine ring system in this particular case by a ring contraction. Alternatively, this beta hydrogen can also be removed and an elimination can take place as it is shown here. So this is something like a Hoffman elimination product is what is formed. So when the reaction is carried out under basic condition, the competing elimination product is formed in about 5 to 25% yield, whereas the 2,3 sigmatropic rearrangement through the ylide is formed to an extent of about 60 to 89% or so. If the same reaction can be carried out in the absence of any base, in other words, if the ylide can be generated in the absence of base-free conditions by a carbene transfer reaction, here the diazo ester is transferring the carbene to the copper, and copper in turn transfers the carbene onto the nitrogen, resulting in the formation of a nitrogen ylide. Now this nitrogen ylide is formed in the absence of any base, so there is no problem of elimination reaction, Hoffman elimination reaction taking place. Only a 2,3 sigmatropic rearrangement takes place to produce the product in very high yield of about 98% or so. So that is advantage of generating the nitrogen ylide without the presence of a base. Another example of a copper mediated intramolecular carbene transfer reaction is what is shown here. This alpha diazo ester undergoes decomposition in the presence of copper acetyl acetonate, resulting in the formation of a copper carbenoid system. The carbene that is generated is now added to the nitrogen to produce the corresponding ylide. This is already substituted with the allyl group here. So the ylide undergoes the 2,3 sigmatropic shift, resulting in the formation of the alpha allyl substituted amine derivative, which is the final product in this particular case. The intramolecular carbene transfer is shown by this mechanism. Nitrogen is electron rich, whereas carbene is electron deficient. So the nitrogen pair is added to the carbene, resulting in the formation of the ylide, which has a structure, a zwitterionic structure, where the nitrogen possesses the positive charge and the carbene center possesses the negative charge in this particular case. Now again, diastereoselective 5-membered cyclic transition state is what is illustrated in this particular example. If we have an equatorial isomer of the allyl nitrogen ylide and the axial isomer of the nitrogen ylide, the diastereoselective rearrangement produces this particular diastereoisomer from the equatorial isomer, and this particular isomer where you have a E isomer of the double bond from the axial isomer of the starting material. So essentially this is selectively found because of the 5-membered cyclic transition state. This is also 5-membered cyclic transition state, except the substituent is an axial substituent, so resulting in the formation of this particular product in this particular case. Now benzyl ammonium salts undergo the benzyl ammonium salts undergo 2,3 sigmatropic rearrangement, which is known as Somley-Hauser rearrangement. If you take a benzyl ammonium salt of this type, which is shown here, this is trimethyl benzyl ammonium salt, or orthomethyl substituted trimethyl benzyl ammonium salt is what is treated with the base. When you treat it with the base, it produces the corresponding nitrogen yelid. The nitrogen yelid undergoes the 2,3 sigmatropic rearrangement with the breaking of the carbon-nitrogen bond and forming of the carbon-carbon bond, which produces this intermediate here. This undergoes tautomerization under basic conditions to give the corresponding tertiary amine, which is shown here by a hydrogen migration reaction. The same reaction is used for synthesis of a medium-sized ringed tertiary amine in this particular case. The base abstracts the hydrogen from the methyl proton, and which generates the nitrogen yelid, followed by attack in the ortho position, resulting in a 2,3 sigmatropic rearrangement to produce this particular tertiary amine. Is also constitutes an example of a Somley-Hauser kind of a rearrangement reaction in this case. Here is another example of a nitrogen yelid being produced alpha to the nitrogen, which is this acidic hydrogen here, resulting in the formation of an yelid. The yelid undergoes 2,3 sigmatropic rearrangement to produce a medium-sized ring, which is a tertiary amine in this particular case. What we have seen in the examples that are shown in the particular module is examples of 2,3 sigmatropic rearrangement. First, we define the 2,3 sigmatropic rearrangement, how it occurs, and what is the Woodward-Hoffmann rule for the corresponding sigmatropic rearrangement, and the nitrogen, sulfur, and selenium systems which undergo the 2,3 sigmatropic rearrangements are illustrated with a lot of examples in this module. Hope you enjoyed the module. Thank you very much for your kind attention.